In the world of AI, there's this constant push for more data, more power, and probably most important of all, more speed. But here's the problem. As our data sets just explode in size, we're talking billions of records, even our best algorithms can get totally bogged down. They can take hours, sometimes even days to train. So the big question is always, how do we get faster without losing all that precious accuracy? Well, let's dive into one absolutely brilliant solution.
Just imagine for a second. What could you do if your machine learning models could train 20 times faster? Seriously, think about it. What kind of new ideas could you test out? What massive, once unsolvable problems could you suddenly take a crack at? It sounds like science fiction, but a team of researchers found a way to do exactly that, and the way they did it is just so clever.
Okay, so to really get what they did, you need to meet the main character of our story. It's a powerful and super popular algorithm called the Gradient Boosting Decision Tree, or GBDT for short. Now, data scientists love this thing because it is incredibly accurate. But it has one major flaw. When you throw big data at it, it can be painfully slow.
So what's the holdup? Why is it so slow? Well, because its traditional method is basically just brute force. I mean, to make the absolute best decision it can, the algorithm literally checks every single data point against every single feature. It's looking for that one perfect place to split the data. Now, with millions of data points and thousands of features, you can probably see how this becomes a massive bottleneck.
Here's what that actually looks like. The algorithm builds this data summary, it's called a histogram, for the first feature. It finds the best split. Great. Then it throws all that work away and builds a brand new histogram for the second feature and finds its best split. It does this over and over again for every single feature. The real time drain, the thing that costs all the time and energy, is building these histograms from scratch every single time.
Right. So this whole situation led the researchers behind a project called LightGBM to ask a really crucial question. Instead of just throwing more computers at the problem, the brute force approach, could they find a more intelligent way to do this? How could they make the algorithm work smarter, not just harder? And they came up with two brilliant hacks.
Okay, hack number 1 is all about focusing on what actually matters. It's called gradient-based one-side sampling, or GAUS. And this idea is all about tackling that problem of having way too much data to check in the first place.
Now, to get GAUS, we just need a quick definition for this word gradient. Don't worry, it sounds technical, but it's really simple. Just think of a gradient as the training error for one piece of data. If it has a large gradient, it means the model's getting that data point very wrong. It's like a hard question on a test. A small gradient, that means the model has already figured it out. It's an easy one.
So, the huge insight with GAUS is this. The old way treated every piece of data the same, which wasted a ton of time going over the easy stuff the model already knew. The GAUS way is so much smarter. It gets that the most useful information, the stuff that really helps it learn, comes from the data it's struggling with. The data with those large errors.
So here's the strategy. GAUS keeps all of the hard examples, those ones with the big gradients. And then, just to keep things balanced, it only takes a small random sample of the easy ones. It focuses all its attention where it's needed most, and that lets it slash the amount of data it has to scan, all without really losing any accuracy. It's genius.
But hey, that only solves half the problem, right? What happens when you have way too many features? Well, that brings us to the second hack. This one's called exclusive feature bundling, or EFB, and it's all about cutting down the sheer number of questions the algorithm even has to ask.
To get this one, we first need to know what mutually exclusive features are. And again, it's a really simple idea. Just think about things that can't be true at the same time. For example, a data point about a person can't say their city is New York, London, and Tokyo all at once. If the answer to "is the city New York" is yes, then the answer for London and Tokyo has to be no. A lot of datasets are just full of these.
So the aha moment for the EFB hack is realizing that checking all these exclusive features one by one is incredibly wasteful. So what does it do? It cleverly bundles them all together into a single, much more efficient super feature. So instead of building 3 separate histograms for our 3 cities, the algorithm can now get away with building just one.
So how does this magic trick work? Well, the algorithm bundles these features by basically putting their values into different, non-overlapping slots. Think of it like this. Feature A gets to use bins 0 to 10, while feature B gets to use bins 11 to 20. By adding a little offset, they can be merged into one big feature bundle that uses all the bins from 0 to 20 without losing any of the original info. And the result?
You build one histogram instead of a whole bunch of them, which just slashes the computation time.
All right, so you take GAUSS, which intelligently samples your data, and you add EFB, which intelligently bundles your features. What happens when you put these two amazing hacks together into one algorithm? You get LightGBM, and the results, well, they're pretty stunning. In their experiments, the researchers found that their new method, LightGBM, could speed up the training process by up to 21 times. Let that sink in. Not 21% faster, 21 times faster than the standard approach. And it did this while getting almost the exact same accuracy. That is a gigantic leap forward.
And hey, don't just take my word for it. Look at this chart. This shows different algorithms training on a flight delay dataset. The vertical axis is accuracy, and the horizontal one is time. Now just look at that solid blue line for LightGBM. It just shoots straight up. It hits maximum accuracy in a tiny fraction of the time it takes the other methods, which are still slowly, chugging along.
And this wasn't just a one-off thing. Check out this table. It shows the time it took to run a single training iteration, comparing the super popular XGB used algorithm to LightGBM. On the Allstate insurance dataset, it's nearly 38 times faster. On the huge KDD10 dataset, it's over 37 times faster. These aren't just little tweaks. These are absolutely game-changing speedups.
Okay, so a faster algorithm is obviously great for data scientists, but why should the rest of us care? Well, because this kind of speed-up has a ripple effect. It's the kind of thing that actually accelerates the entire field of AI and everything it touches.
Here's what this really means in the real world. Faster experiments? That means researchers can try out way more ideas way faster, which leads to quicker discoveries in medicine, finance, you name it. It means we can finally start tackling problems with datasets that were just too massive to even think about before. It also makes powerful machine learning more accessible to students and startups who don't have a basement full of supercomputers. At the end of the day, breakthroughs like this just speed up the pace of innovation for everybody.
And that leaves us with a really fascinating thought. This incredible speedup didn't come from a bigger, faster computer. It came from two clever ideas that just completely reframed the problem. It really makes you wonder, right? What other huge, complex problems out there aren't waiting for more brute force, but are just sitting there, one clever shortcut away from being solved?